Oh, it's my great pleasure to introduce Professor Nikhil Srivastava from UC Berkeley. The title of his talk is Ramanujan Graph and the Interlacing Family. Professor Srivastava is the recipient of the Frontier of Science Award of this year. Also, I don't know him very well, but I know his co-author, Dan Spielman. Actually, the Spielman wrote some very good lecture note, and I used many years ago used some of his lecture note in my special class course. Okay, please.
Thank you. Thank you for the generous introduction and for this invitation and organizing this wonderful conference. This is a talk about work that's around 10 years old now, and so I'm not going to try to tell you the proofs of these results. Instead, I'm going to try to survey what's happened since then and what are some of the connections between this work and more recent developments in adjacent areas of math. It's based on joint work with Adam Marcus and Dan Spielman. Please do stop me at any point if you have questions. So here's an outline of the talk. So I'll begin by motivating the study of Ramanujan graphs from two different contexts. So the first is spectral graph theory, and the second is random matrices. Then I'll introduce the main kind of new technique in our work, namely interlacing families, which allowed us to make progress on this question of existence of Ramanujan graphs. And I'll talk about the key object in that technique, which is the expected characteristic polynomial of a random matrix. After that, I'll apply this technique to two different models of random matrices. The first model is random covers of a fixed graph, which I'll define at the appropriate time. And the second is simply random regular graphs. And in each of these settings, we'll get some results about Ramanujan graphs. Then I'll talk about some generalizations of these results that have been done by other people since this work originally appeared, and I'll end with a number of open problems. So what's the context for the study of Ramanujan graphs? So the first kind of context is spectral graph theory, which is an area where you study graphs, which are combinatorial objects, by looking at spectra of their adjacency matrices. And specifically, there's this important subject of expander graphs. So I'll define it precisely in the next slide, but maybe I'll show you some pictures first. An expander graph conceptually is a very sparse graph, so let's say constant degree, which is nonetheless very well connected. So on the left here, you have some examples of graphs that would be considered expanders under any of the many reasonable definitions of expansion. The first one is a Peterson graph. The second one is some kind of a random graph. And on the right, you have graphs that are not expanders, namely the grid graph and the cycle graph, and they're sparse, but they're not well connected. You can partition them into roughly equal sized sets, cutting very few edges. Okay, so the definition of expansion that we're going to be interested in is spectral expansion. So we're going to look at undirected d-regular graphs on n vertices. So given such a graph G, you can look at its adjacency matrix, which is a symmetric n by matrix, and it has n real eigenvalues. And throughout the talk, I'm going to sort them in this order, where lambda 1 is always the largest eigenvalue and lambda n is the smallest eigenvalue. Now the graph is d-regular, which means every row of this matrix has d1s, and so the all ones vector is an eigenvector with eigenvalue d, and you can check that that's the top eigenvalue. So the top eigenvalue is always d. So that doesn't really tell us anything about the graph other than it's a reflection of the fact that it's regular. But now if you look at the other eigenvalues, they start telling you interesting combinatorial things about the graph. So maybe the first fact in spectral graph theory is that the graph is connected if and only if the second eigenvalue is strictly less than d. And then another easy fact is that the graph is bipartite if and only if the bottom eigenvalue is equal to minus d. So these eigenvalues of d, and when the graph is bipartite minus d, they don't really tell us anything that interesting about the graph, so I'm going to call them the trivial eigenvalues. And the definition of spectral expansion is kind of a quantitative version of this first fact, that the graph is connected if and only if the second eigenvalue is less than d. The definition is, well, a graph is a spectral expander if for all of the non-trivial eigenvalues, that means ignoring the d eigenvalue and minus d for bipartite, all of them are bounded away from d in absolute value. So they're concentrated away from the ends of this interval minus d. and the further they are from D, the better expander I'm going to call the graph. And what I mean by this less than is that the eigenvalues should be uniformly bounded away from D, independent of the number of vertices of the graph. Okay, so that's a definition of a spectral expander, and it raises a natural extremal question, which is, given a particular degree D, like 3, let's say I look at 3 regular graphs, how small can I make these eigenvalues? How good an expander can possibly exist given this degree constraint? So any comments or questions on this so far? Okay. So this brings us to the definition of a Ramanujan graph. So it turns out that there's a limit to how concentrated the spectrum of a D-regular graph can be. It's given by this well-known result called the Alon-Bopana bound, which says that if you have a connected D-regular graph, then the second eigenvalue is always at least this very special number 2 square root D minus 1 minus some little o of 1 as the number of vertices of the graph goes to infinity. Okay, so this number is going to keep appearing again and again in the talk, and it has a conceptual meaning. The conceptual meaning is related to the infinite D-regular tree. So the infinite D-regular tree is an infinite graph. It's a tree. Every vertex has degree D, and you can look at its adjacency matrix. It's a bounded operator. It has a spectrum, and the spectrum turns out to be exactly this interval minus 2 square root D minus 1 to 2 square root D minus 1. And so what this Alon-Bopana bound conceptually is saying is, in some sense, this infinite D-regular tree is the best spectral expander. You can never concentrate eigenvalues of an infinite sequence of graphs on any interval smaller than the spectrum of this tree. And this tree is naturally related to D-regular graphs in the sense that it's the universal cover of every D-regular graph. So the Alon-Bopana bound says you can never have spectral expansion better than this bound. And that leads us to the definition of Ramanujan graph. So D-regular graph is Ramanujan if for all non-trivial eigenvalues they are contained in this interval, minus 2 root D minus 1 to 2 root D minus 1, the spectrum of this infinite tree. So in the picture, I want everything to fall in this red interval here. So that's the definition of a Ramanujan graph. So any questions, comments on this definition? Okay. So what we're interested in this area of spectral expansion is constructing infinite sequences of graphs that are Ramanujan. And a highly non-trivial result is this theorem of Margulis and Lubotzky-Phillips-Sarnak from 1988 with an improvement, with a kind of generalization due to Morgenstern, which says that if D is a prime power plus 1, so for certain degrees, there are infinite sequences of Ramanujan graphs. And these graphs that they construct are certain Cayley graphs of PSL2 FQ, where Q is some other prime chosen carefully depending on P. So this theorem says Ramanujan graphs exist, but only for some sporadic degrees. And this is actually where the terminology Ramanujan came from, because the proof of this involves the Ramanujan conjectures in number theory. So the first motivation for the work that I'm going to present is this question, which was, as far as I can tell, raised by Lubotzky in 1994, which is, well, what about other degrees? So in this theorem, you need the degree to be prime power plus 1. Do they exist for all degrees? So that's the first context for this talk. The second one is random matrices. So now we just switch gears and we think about random graphs. So fix a degree D, that's at least 3, and let G be a random D-regular graph, so uniform from the space of all such graphs on n vertices. So here, what I did is I went in MATLAB, I generated a random 5 regular graph on 50 vertices, and I plotted its eigenvalues, and they end up looking like this. So there's a trivial eigenvalue of 5, and it looks from this picture that all the other eigenvalues are between 2 square root 5 minus 1 and minus 2 square root 5 minus 1. This is MATLAB. They're not integers. These are bins in a histogram. Yes, they're not integers at all, for sure. Okay, so this was an experiment, but there's a famous theorem due to Friedman from 2008, which proves the conjecture of Alon. And what he proves is that, well, actually, this always happens with high probability, or almost always happens. He shows that you take a random D-regular graph, and with high probability, all of the eigenvalues except for the top one are actually bounded by this Ramanujan number plus little of 1. The little of 1 was 1 over polylog n in his proof. And there have been other works about this in the years since then, but there's actually quite a bit of excitement about this in the last few months. So there are these two major improvements of this result that appeared in the last 2 months, as far as I can tell, within a week of each other. So by people in this room. So first is the result of Chen, Garza, Vargas, Trop, and Van Handel, who improved this 1 over poly log n to 1 over poly n, and gave a completely different proof that was very short, kind of very conceptual proof. And then around the same time, Huang, McKenzie, and HTL improved this to n to the minus 2/3, which is actually the optimal possible bound, which is related to the Tracy-Witten law. So we now have a very sharp understanding of what happens with high probability for these random irregular graphs. So all these results are with high probability. Okay. I should mention there's another random model that's been heavily studied in recent years, which is not random regular graph. This is the model of random n covers of a fixed graph. So I'll define precisely what this is later, but roughly speaking, it's you take a fixed graph and you replace every edge by a random n by n permutation matrix. And there's this very influential result of Bordenoff-Collins from 2019, who showed that if you take a random n cover of a fixed Ramanujan graph, then all the eigenvalues are also almost bounded by they're almost Ramanujan. Okay, they proved something more general, but this is one consequence of what they proved. So these results all hold with high probability, and they all have this little o of 1 term. So a natural question you can ask is, well, can this little o of 1 term be removed? And it's known, or it's believed, and it's certainly, you can check experimentally, that if you want to remove this little o of 1 entirely, you cannot hope to prove something with high probability. You can only hope to prove something with constant probability. And so this is the second question: can you remove these little o of 1 in these results if you settle for a lower probability? Any questions or comments on this? Yes. Yeah, it's related to the proof of the spectral bound for the Lubotzky-Phillips-Sarnak graphs, which is related to the Ramanujan conjectures in number theory. They named them that. Any other? Okay. Okay. So now what I'm going to do is I'm going to present one particular device that called interlacing families, which we'll use to address these questions to some degree. Okay, so the key idea here, or the key object actually, is the expected characteristic polynomial of a random matrix. So suppose you have a random matrix R, let's say it's Hermitian. I'm not specifying what the model is. We'll consider many different models in the talk. What I can do is I can simply consider the univariate polynomial. That's the expectation of the characteristic polynomial, right? So the characteristic polynomial is determinant of Z identity minus R. And I just take its expectation, coefficient-wise, as a polynomial. Now, if you expand this characteristic polynomial in elementary symmetric functions of the matrix R, what you see is that this is just some kind of a generating function whose coefficients are the expectations of the elementary symmetric functions of the random matrix. That's what EK of R means. So this is a univariate polynomial. This is not the first time these things have been studied. They appear in the book of Mehta, for example. But we'll kind of use them in a different way than they've been used before. So any questions about what this is? So this is like the main object in this talk. Okay. And so each of the characteristics. So for any fixed R, this characteristic polynomial of R is a polynomial with real roots because it's a Hermitian matrix. But when you average over all realizations of R, you're averaging a bunch of polynomials with real roots. You may not get a polynomial with real roots. In general, this polynomial does not have real roots. The other thing I want to say is that comparing to what we usually do in random matrix theory, many of the results I showed in the previous slide are based on computing expectations of traces of powers of R, so that's moments of the eigenvalues. And here, somehow, we're computing expectations of elementary symmetric functions of the eigenvalues. Okay, so the main theorem about this object is this thing called theorem C, which is C for comparison. And it's really a bunch of theorems, but I've just condensed it into one statement here. So the statement is for certain models R, where there's a lot hidden in the word certain. I'm not actually going to tell you what certain is, but there's some class of random matrix models R for which the expected characteristic polynomial is real rooted. So all the roots are real. So that's a special property. And the eigenvalues of the random matrix R can be compared to the roots of the expected characteristic polynomial in this manner. So for any index I, so let's say I is 1, so the top eigenvalue, the probability that the largest eigenvalue of R is bounded by the largest root of this expected characteristic polynomial is positive. Okay, there's no bound on the probability. It's just saying that there exists at least one point in the sample space such that this inequality holds. Okay, now this looks very close to a statement which is trivial, which is Markov's inequality or something like that. Right? So if I put the expectation outside the lambda I of the characteristic polynomial, this is kind of trivial. But the whole point here is that I'm looking at the expectation with respect to the coefficients, and I'm able to relate the roots, the eigenvalues of the matrix to the roots of the expectation, which is not the same thing as the expectation of the roots. Okay. So, I mean, there are two reasons why this theorem is effective. So one is that the statement is weaker than the typical statements of random matrix theory. It proves something happens with positive probability. And as a result, it can potentially prove things that don't hold with high probability. It can actually, there are cases when you can use it to prove things happen which are actually rare. And the other is that it's just a completely different type of, this computing expectations of elementary symmetric functions turns out to be much easier to do than computing expectations of traces of powers of the matrix generally. So any comments or questions on this? Okay. Okay, so I won't prove this for you because, well, I haven't even exactly told you what the theorem is because I haven't told you what certain is. But I'll tell you what the main ideas in this proof are. So the seed of this theorem is the following very elementary lemma about a pair of real-rooted univariate polynomials. So suppose you have two polynomials P0 and P1, which are monic polynomials of degree n, such that all their roots are real. And suppose you further have this property that not only are the roots of the individual polynomials real, but the roots of all convex combinations of them are also real. So let Pt be the convex combination of these polynomials with coefficient t. So that's the assumption. You have real rootedness of all convex combinations. Then the conclusion is that, you know, the ith root of the average of the two polynomials, so this is some overkill notation for just saying I average the two polynomials coefficient-wise, is always contained in the convex hull of the ith roots of the individual polynomials. So here's this picture. There's a blue polynomial and a red polynomial. Okay, let's assume they satisfy the hypothesis of this theorem that all convex combinations are real rooted. What it's saying is if you average these polynomials in any way, actually, then the roots of the average have to fall in these yellow intervals. Okay. So this is an exercise, and you can do it now if you want. You can do it later, but if you want to get a sense of how this area works, this is a very simple exercise for you to do. It's essentially the key thing is that the roots are continuous in the coefficients. That's essentially what it is. But it's very powerful because it allows you to average polynomials coefficient-wise and yet reason about what happens to the roots, and the mapping from the coefficients to the roots is some highly nonlinear mapping. Okay, so once you have this lemma, then you can go about proving theorem C. Now, the input to this lemma is proving that certain convex combinations of some polynomials have all real roots. And in order to apply this, to obtain the same kind of conclusion for expected characteristic polynomials of complicated random matrices, you need to do some work, but at a very high level, it's just induction. You inductively apply statements like this in some very specific ways to build up this much more complicated average of polynomials, the expected characteristic polynomial of your random matrix. And the object that kind of coordinates this is called an interlacing family. And I'm not actually going to tell you what that is. It's just some inductive way of applying this lemma But as you do this, you keep having to establish that certain polynomials have real roots, and to do that, you do need some machinery, and the relevant machinery is the theory of real, stable, and hyperbolic multivariate polynomials. So this is some old subject that goes back to the 50s. It started with the work of Gording and was also studied by Ruel, Lieben, Sokal, Gurvitz, and most recently Proche and Brantain. And this is a multivariate theory of real rootedness. In particular, it gives a complete understanding of which linear transformations of multivariate polynomials preserve some multivariate analog of real rootedness. And this is the key input that's used to prove theorem C. Eventually boils down to things like this level. And that's a picture of the the zeros of a hyperbolic polynomial, which I also haven't. But this is roughly how the proof of theorem C goes. So any questions or comments on this? Okay. So once we have this theorem, we can now apply it to study some certain random matrices R coming from random graphs. So the first model we study is random covers of a fixed graph. Okay, so let me define what this is. So fix some degree at least 3 and let G be a deregular graph on n vertices. Okay, that graph is not regular, but it's good enough for illustration. So what's a 2 cover of G? So 2 cover of G is another graph H, which is also deregular, but it has twice as many vertices, 2n vertices, and I'm going to define it constructively, like very combinatorially, as follows. So a 2 cover H is constructed by creating 2 copies of this base graph G. Let's call them G1 and G2. And then for every edge in the original graph, replacing the 2 edges in these 2 copies either by parallel edges or by crossed edges. So in this example here, I've replaced 2 of the edges in G by crossed edges in this 2 cover H. Okay, it is also just a cover in the sense of topology, but this is a very concrete combinatorial description of how to construct a 2 cover. So if there are m edges in the graph, there are 2 to the m 2 covers that could possibly be constructed. And this has a very simple description if you look at the adjacency matrix of the graph. So the adjacency matrix of a 2 cover H is simply obtained by taking the adjacency matrix of the base graph G, and replacing every non-zero entry by a 2 by 2 permutation matrix, preserving the symmetry of the matrix. So any questions about what a 2 cover is? The 2 cover of a graph. Okay. So it's a way of taking a graph and getting a bigger graph with the same degree. And the nice thing about these 2 covers, which is an instance of a more general fact, is that the eigenvalues of a 2 cover are simple to describe. The set of eigenvalues of the 2 cover H is equal to the eigenvalues of G, which I'm going to call the old eigenvalues, along with an eigenvalues of a related matrix A sub S, which is a signing of the adjacency matrix of G corresponding to the permutations that I chose. So the signing A sub S of my base graph is a matrix that has a +1 for an edge if I kept the edges parallel, and a -1 if I cross them. So it's an n by n matrix. And this is a linear algebra exercise that the new eigenvalues that I get when I take this 2 cover are simply the eigenvalues of the signing. Okay, so this object, this idea of using 2 covers was investigated by Bilou and Lineal for this problem of constructing infinite sequences of Ramanujan graphs. Because suppose you could, find a 2 cover given a graph. Suppose you could find a 2 cover where all of the new eigenvalues were small. Well, then now you have a bigger graph, which, if the original graph was Ramanujan, is also Ramanujan, and then you can keep repeating this to get an infinite sequence. So they made the following very bold conjecture. Every deregular adjacency matrix A has a signing such that the eigenvalues of the signing are contained in this interval, this Ramanujan interval. And if this is true, it implies, just by applying it repeatedly, starting with a fixed Ramanujan graph, that there exist infinite sequences of Ramanujan graphs for every degree less than or equal to greater than or equal to 3, which answers this question of Lubotzky. So this was a very beautiful conjecture made by them. They couldn't quite prove it. They proved it up to some polylog d factor, which is a little bit large for the the formulation of the problem we're considering. And the first theorem I'm going to tell you about is a proof of partial resolution of this conjecture. So theorem A, which says every d-regular adjacency matrix A has a signing such that the top eigenvalue is upper bounded by 2 root d minus 1. Okay, so the difference between theorem A and the conjecture is it doesn't control the full spectrum, it only controls the top of the spectrum. Now, it turns out that this theorem implies that there are infinite sequences of bipartite Ramanujan graphs for every degree at least 3. And this is because the eigenvalues of bipartite graphs are symmetric about 0. So controlling the top is equivalent to controlling the bottom. But before I tell you about the proof, any questions or comments on this statement of the theorem? Yes? My understanding is they did numerical experiments also, yeah. And so yeah, you can write code that finds these things, although we don't know how to prove it. But I don't know. Does anybody know how they made this conjecture? Anyway, yeah. Any other? Yes. Yeah. So for this infinite sequence, the seed graph can just be taken to be the complete graph. So the complete graph on d vertices is Ramanujan. Yeah, it's related to connection Laplacians and things like that. Yeah, that's a good point. It's the same. I'll talk more about that later too. Yeah. Okay. Okay, so let me tell you how to prove this theorem. So what is the proof? So consider a random signing of the base graph. So we have a base graph. It has an adjacency matrix A. Let A sub S be a random signing of this adjacency matrix. Now by theorem C, it's enough to control the largest root of the expected characteristic polynomial of this random signing. I'm hiding a lot here, right? Because implicitly I'm saying that this random matrix satisfies the assumptions of theorem C, but it does. So theorem C reduces this problem to simply controlling the roots of this one univariate polynomial, the expected characteristic polynomial of a random signing, and showing that it's bounded by 2 squared t minus 1. Okay, so this will be done in 2 lemmas, none of which we even had to prove. So the first lemma is a theorem of Gottsel and Gutman from 1981, where they did this computation. They showed that for a d-regular graph with adjacency matrix A, it's actually true for any graph, if you take a random signing A sub S, then the expected characteristic polynomial is just equal to an object in algebraic combinatorics called the matching polynomial of the graph. So the matching polynomial of a graph, mg, is this univariate polynomial. For a graph on n vertices, it has degree n. And the coefficients simply count the number of matchings of various sizes in the graph. Okay, so yeah, I mean, it's a generating function that counts the number of matchings of different sizes in the graph. This is the paper that this is taken from. This is actually quite easy to prove. If you're looking for a second exercise to do, you can try doing this. This is also quite a pleasure to prove. It's harder than the first one, but yeah. Okay, so this is a formula, or not a formula. This is a computation of this object that shows that it has some interpretation in terms of matchings. Okay. That's lemma 1. So now all we have to do is figure out how big are the roots of the matching polynomial. But this was done 10 years earlier by Hellman and Lieb in 1971, where they proved this result. For a graph of maximum degree d, the largest root of the matching polynomial is bounded by 2 squared t minus 1. Yes? Yes, it is interesting. Yeah, the first so you can prove something stronger. You can get 2 root t minus 1 minus order 1 over n. You can get that. I don't know what the right bound is. Actually, no, sorry. Minus 1 over n to the 1/6, I know how to get. So Hermite polynomials are a special case of this. And that presents some obstacle. Yeah, so the best I know is minus 1 over n to the 1/6. You're right, so it's interesting. So, but anyway, for this application, all we need is this, and this was studied. This is called the monomer timer partition function, and this is proven. And this number is not a total accident that it's the same number that comes from the infinite tree. The proof of this theorem comes from some kind of tree recursion related to log derivatives of this polynomial, and there's a tree of degree bounded by d that appears in this proof. So that actually completes the proof. So given theorem C, these known results simply prove this theorem. Any questions or comments on this? Okay. I should say that was about 2 covers. There's a natural generalization to k covers. So in a k cover, you replace every edge by permutation of a k by k permutation. And there's a beautiful paper of Hall, Puter, and Sawin, which proves that this more general result that actually for every k, every d-regular graph has a k cover, which has new eigenvalues bounded by 2 root d minus 1. Okay. So summary of what just happened. Well, we started with this sorry, to say lambda 1. We started with this random matrix A sub s, which is a finite dimensional random matrix. And then we related it to this expected characteristic polynomial, which is a polynomial. But then this somehow served as a bridge to this infinite object, which was the infinite irregular tree. And that's where we got this upper bound of 2 root d minus 1. And this bound was sharp because actually, if you look in the proof of the Elon-Bapana bound, it also comes from this infinite irregular tree in some sense. So whatever bound you get from this has to be sharp because the same object is appearing on both sides of these inequalities. Okay, so that's the first model. Let me now briefly describe another model of random graphs, which can be analyzed using this technique, but goes in a somewhat different direction. So this is a model of random regular graphs. So it's not uniformly random regular graphs. It's the following. So fix the degree d and let n be even and take d independent random n by n permutation matrices. So P1 through Pd. And now fix M to be the adjacency matrix of a matching on n vertices. This is why it took n to be even. So it's a perfect matching. So it looks like this. So the characteristic polynomial of this matching is it's very easy. It's just z squared minus 1 to the n over 2. The eigenvalues are plus 1 and minus 1. And now the random graph model I'm going to consider is just a sum of these, d matchings conjugated by these random permutations. Okay, so take the matching, I conjugate it by random permutation, I get something that looks like this. I do this d times, I add them, I get a multi-graph. Okay, so it may not be a simple graph, edges may be repeated. So that's some model of d-regular multi-graphs. And the theorem that can be proven about this is that with non-zero probability, the second eigenvalue is bounded by this Ramanujan bound. And this implies that there are bipartite Ramanujan multigraphs of every degree and every size when n is even, and every even size. The star is because this is not as obvious an argument as in the previous case. Some work is required to get this, but does imply this. So any questions or comments on this? Yes? Excuse me? No, it doesn't have loops, but it can have multi-edges. It's not the configuration model, yeah. Actually, no. So I did try to do that a little bit, and it's not clear how to do it. It's a nice kind of a, yeah, like it's a nice problem. I don't know how to get simple graphs. Yeah, but you could try this in the configuration model or other models. It's a natural thing to try to do. Okay. So how does the proof of this go? Well, the sketch is kind of similar. Consider this random matrix. By theorem C, again, this satisfies the assumptions of theorem C. It's enough to prove that the second root of the expected characteristic polynomial is bounded by this number 2 root d minus 1. And this is now done in 2 lemmas, which were not previously done. The first lemma shows that this expected characteristic polynomial is actually equal to a known object, which has been studied in as early as 1922 in the context of invariant theory. It's called the Walsh convolution of polynomials. I won't tell you what it is, but it's some very explicit bilinear operation on polynomials with an explicit formula. And the proof of this has some invariant theory type argument. It uses the fact that this random matrix model has a lot of symmetry. Namely, you can, it's invariant under some action of permutation, right? And so this somehow enters into this polynomial, and it ends up being this kind of very specific known object. So the Walsh convolution is a bilinear operation that takes 2 degree n polynomials and outputs another degree n polynomial, which and it preserves real rootedness. Walsh proved that. So in particular, this thing has real rootedness. Okay. The second lemma is useful in analyzing the roots of this d-wise convolution. Sorry, so what I meant to say is that the expected characteristic polynomial is a d-wise convolution of just the characteristic polynomial of a matching, which is a very simple object that I wrote on the previous. Okay, so now we need to analyze the largest root of this. How do we do that? Lemma 2 says that the second root of this d-wise convolution is actually bounded by the edge of the support. So lambda 1 on the right-hand side means the edge of the support of a certain probability measure. Probability measure is mu1 free convolution with mu1 d times. Okay, I'll say a little bit about what free convolution is in a moment. It's an operation defined by Lubotzky on probability measures. And mu1 here is just the uniform measure on the eigenvalues of a matching. So it's uniform measure on +1 and -1. Okay, now what is the point of this? So, I mean, I don't have time to precisely define what this free convolution of probability measures is, but it's in particular, it is the limiting spectral distribution of the same random matrix model as n goes to infinity. Okay, so everything that's written above on the slide is for finite n, right? At fixed n, I've looked at the expected characteristic polynomials. I got this formula in the Walsh convolution. What this is telling me is that the roots of this polynomial of degree n are upper bounded by the edge of the support of some probability measure, which is obtained by taking a weak limit of this same kind of spectral distributions, but as n goes to infinity. Okay. And once you have this lemma, then it's a kind of standard homework exercise in free probability to calculate what the right-hand side is, and magic, no surprise, it's 2 square root t minus 1. So this measure, it turns out to be the Keston-McKay law, which is another important measure. And that completes the proof. So it's overall same kind of scheme. You analyze the expected characteristic polynomial, but the tools that came in to do the analysis were somewhat different, making contact with this subjects of invariant theory and free probability. Any questions or comments on this? I certainly didn't give much detail here, but please, yes. Yes, that's right. The roots of the matching polynomial are symmetric about 0. Yeah. Any other? Okay. Okay. So I want to add, say, there is actually a connection between this theorem and theorem A, the theorem about 2 covers of graphs, which use the matching polynomial. It turns out there's a totally different proof of this theorem, which is not how we proved it, but this is how Hall, Puder, and Savin proved it. You can view this random graph model as being a random n cover of, am I missing a slide? Oh, I'm sorry, of this graph, a vertex with d edges. If you take a random n cover of this graph, you get exactly this random graph model. And so actually, the result by Hall, Puder, Savin also implies this theorem by a completely different proof that goes via matching polynomial. So that's one commonality between the 2 theorems. There's one important difference, which is more from a computer science angle. So there's a result of Michael Cohen from 2016, which says that for theorem B, namely these multigraphs, there is a polynomial time algorithm which can find them in time polynomial linear. However, for theorem A, we don't know any efficient algorithm. So somehow the computational difficulty, the complexity computationally of these 2 constructions seems to be potentially different. Okay. Any comments or questions on this? Yes. Is the algorithm deterministic? Yeah, so Cohen's algorithm is deterministic. Yeah. Yes. Nothing about lambda n. So in all, I mean, okay, in all these, including in this theorem, there's some further work you can do to get bipartite graphs, and then you get lambda n for free, but nothing known for lambda n. This is just not known. Okay, that's what I want to say about random regular graphs. So I'm running out of time. Let me briefly comment on two generalizations. The first generalization is, can we go beyond trees? So this number 2 root d minus 1 arises because the infinite d-regular tree is the universal cover of every d-regular graph. But you can ask this question, well, what if I have some other infinite graph that's not a tree? When does it have infinitely many quotients such that the largest non-trivial eigenvalue of the quotients is upper bounded by the spectral radius of the infinite graph? So here's an infinite graph. Okay, it's not infinite, but you can imagine how it becomes infinite. That's not a tree. This question was studied by Mohanty and O'Donnell, and they proved a theorem saying they identified a class of graphs, a certain quite special class of graphs, which they call additive product graphs, and they showed that actually all such graphs do have infinitely many quotients that are Ramanujan with respect to that graph. And the proof is very beautiful. It directly relates the moments of the roots of the expected characteristic polynomial to the moments of a certain spectral measure of this covering graph, using this very combinatorial device, which is the theory of heaps of pieces, which is basically a combinatorial interpretation of Newton's identity. So it's a moment of uniform measure on the roots of the polynomial. Yeah, sorry. That's a very nice paper that opens up some avenues for further exploration. Another direction, which is very nice, is, well, you know, a K cover of a graph is something you get by replacing the ones in the adjacency matrix by K permutations. But you could actually you could do something more general. You could look at a group and some unitary representation of the group, and you could consider labeling the edges by these unitary matrices that come from the representation. And this was studied by Hall, Puter, Sawan, and they gave some sufficient representation theoretic conditions to prove this more general theorem that generalizes the theorem about signings. Namely, if you have any d-regular graph, and if you have a group, you have a representation that satisfies certain properties, then you can do a signing by these unitaries that come from the representation and still get the Ramanujan graph. And one question that was raised in their paper that seems very pertinent to this area is, what about this specific group that was used in the original construction of Ramanujan graphs? And we simply don't know the answer to that. But they have a number of other groups that we don't know the answer to this question for. Okay, so I'll end with 5 open problems. So here are some open problems. So one of them is the one you mentioned. This lambda n thing is completely open. Many people have tried. We don't have any idea how to do it. So do non-bipartite Ramanujan graphs exist for d greater than equals 3? We don't know. We showed the probability is positive in like a very kind of weak sense. It could even be exponentially small. Are there interesting classes of graphs for which you can prove bounds? Can you attack this question of getting bounds in the probability? More recent development, there's this breakthrough result of Hyde and McGee who studied random covers of hyperbolic surfaces. And what they showed is that such a random cover is almost Ramanujan, which in this context means that the new eigenvalues are almost bounded by the bottom eigenvalue of the hyperbolic plane, which is the universal cover of such surfaces. So basically, they proved an analog of these little O1 results, but for random surfaces. And a key input in their proof was this result of Bordunov-Collins, which I mentioned. And so one speculation is this at all relevant to understanding this area of eigenvalues of random surfaces? There's this question about signings by elements of PSL2FQ that I already mentioned. And finally, there's a computer science question, which is, can you find Ramanujan signings of graphs in polynomial time? So we don't know. The best known bound is exponential in n to the 1/3, which is surely not the right answer. And if you could do this, this would have applications to other questions in discrepancy theory and related questions. So that's it.
Question?
Yes.
If my memory is correct, I think you mentioned we can study eigenvalues, second largest eigenvalues by the moments, the power of trace of these matrices. So could you be a little bit more specific about the difference between the moment method and the method using characteristic polynomials?
Yes. Okay. So your question is about what is the difference between the studying, let's say, the norm of a random matrix using moments versus studying. So it's kind of going back to this slide, right? This comment here, yeah. Versus expected characteristic polynomials. Well, okay. So usually, if you want to bound the norm of an n by n matrix, usually you need moments that depend on n in some way, usually, and so usually there's a weakness of the moment method, which is that if you're going to control the norm by controlling very high moments of the random matrix, that can only be used to prove high probability bounds, unless you do some further conditioning to remove tangles or things like that. So that's somehow a technical difficulty that arises in the moment method, which makes it not impossible but difficult to prove bounds that don't hold with high probability. And so one difference between this method and this moment method is that it's kind of in a different. It's not really a probabilistic argument. I mean, I didn't tell you the proof of theorem C, but it just proves that some probability is positive, right? So it's able to access these very rare events. Maybe that's the answer.
Thank you.
Yes. I mean, I can tell you what the bottleneck is. Like, the bottleneck is that this theorem only applies to one eigenvalue at a time. So you can do all kinds of tricks to try to control two eigenvalues, but you always lose something. So the bottleneck is this theorem C. It's not the stuff about calculating the bounds on the roots or anything. Oh, I mean, is it true? I'm sure it's true. Yeah, you can do that, but you lose a square root 2. You can do that. Yeah. I mean, I think these random covers should give it. You just need a different analysis that allows you to control both sides of the spectrum. Yeah.
So
yeah.
The local bound says that the non-trivial eigenvalues are 1 below
Yes.
by 2 square d minus 1 minus little o.
Yeah.
Freeman's theorem said they're bound above by 2 square d minus 1 plus little o.
Yes.
Then you said, well, why don't we just remove the o1? But what's so special about the value 0?
Yeah, I see.
Why not go below 2 square
That's right.
Does the value 0 have any special significance? Because people obsessed with Ramanujan Graph, but I've never understood what the value 0 is.
That's a good point. So your question effectively is, can you get these so-called super Ramanujan graphs with eigenvalue bounded by 2 root d minus 1 minus something? Yeah. So there's some area in which this is important, like Peter Sarnak was talking about in one of his talks. And I didn't mention this, but the theorem B actually does prove something a little bit stronger. It proves 2 root d minus 1 minus order 1 over n.
1 over n.
Yeah. But I don't know what the right. But you're right. I mean, I don't think there's anything that's special about 0 other than that it's easy to state, and in the limit, that's what you get. But this is you could go in this direction, and it's not. It's related to what you asked.
The number theoretic construction doesn't also give you some extra.
It's a good question. So I talked to Peter about this. It does actually. I don't know if it gives the same exponent or not. It does give something. You need to sweat a lot, but it gives something. Yeah.
So you mentioned the improvement in going from the trace to the symmetric functions, that it simplifies matters, and it seems philosophically related to the improvement, say, in that Bordenave showed in analyzing the non-backtracking walk instead of the random walk, where somehow you avoid a lot of noise coming from repetitions. So in the trace, you have this repetition that you avoid in the symmetric functions. In the non-backtracking walk, you avoid, you know, especially in these high girth graphs, all these returns. And so going to the non-backtracking walk also was important in my work with Lubotzky, that somehow it really simplifies matters. And I wonder if there can be a more explicit connection between these two simplifications.
That's a very good question. So there's a certain, okay, so I can tell, I didn't say this in the talk, but yeah, one, so in some for some random matrices R, the benefit of this object is that it actually cancels out the matrices that have large eigenvalues. So it's actually relying on some kind of cancellation. For example, if R is a diagonal matrix, the expected, I mean, yeah, okay. So there are some other problems, like the Cadison-Singer problem, where you have some random matrix, and you want to prove that it has small norm with positive probability, and most of the time it does not have a small norm. And this object somehow cancels out all of the large norm points in the probability space. There's some vague intuition that it's because they have some Poisson tails instead of the random matrix kind of tails. That is some mechanism which, as far as I can tell, is different from the mechanism appearing in non-backtracking walks. So the non-backtracking walks, I mean, many people here understand this better than I do, allow you to get rid of tangles and things like that. But I don't know if non-backtracking walks have this type of mechanism in them as well. So my sense is that they're probably not, that they're not that closely related for that reason.
Okay. Since the organizer only give me 15 minutes for one talk, so if you have more questions, you can talk with professor after his talk. Okay. Let's thank the speaker again.